might kick off with just kind of, yeah.
Absolutely. Let's get started. Thanks, everyone. Really appreciate your time here. So today we will be talking about Databricks Unified Data Analytics platform with a heavier focus on machine learning and MLOps, talking through what does actually make a machine learning pipeline. And then I'll hand over to Joshi, who's going to take you through an end-to-end machine learning demo. Hey, Joshi. A machine learning demo from data ingestion through all the way to inference. But before we get started, I wish you all are safe during the pandemic and you've adjusted to the new normal, and wish you and your loved ones health and happiness. Let's get started. A little bit about myself. I'm Koorosh Lohrasbi. I'm the CTO at Intellify. I joined Intellify around March. I'm an ex-Amazonian. I was an enterprise solution architect at Amazon for more than 4 years, looking after a number of large enterprise customers. Also, I was focused on machine learning. Co-founded a meetup group, Sydney Machine Learning Meetup Group, which we now have more than 5,000 members, and I was very active in the community and learned a lot from those communities. Kika started a bunch of initiatives back in AWS around machine learning in ANZ and APAC level, but more than everything, I had the pleasure of working with a lot of enterprise customers around adopting machine learning as a widespread enterprise program, rather than just doing a number of disjointed proof of concepts. There has been a lot of learning, there has been a lot of battle scars, a lot of recommendations that we've made to customers, and customers basically applied and probably didn't work out the way we intended. But that is mainly because of the immaturity of the machine learning in production market, which we're going to address some of these issues today. Been in the industry for about 18 years. I started my career as a sysadmin looking after Microsoft workloads, and then worked my way through system engineering and system design and architecture. Always had a need for getting in front of customers and translating business requirements to technical aspects, and making sure that the actual ROI of a certain technology stacks up. So that's me. I'll hand over to Joshi.
Hello guys, I will just do a much briefer one than Koorosh ones. So I spent 3 years as a cloud engineer specializing in big data and machine learning in AWS, and then I moved on to Intellify, trying to delivering the solutions for data engineering, building data platform, and also trying to roll out the MLOps and ML solutions as well. It's an honor to actually having this workshop and walk you through the demo in the next few slides, if we can. Thank you very much.
Excellent. Joshi actually undersells himself. He's one of the unicorns that we have in the team. You can pretty much parachute Joshi into any project, and you have the full trust of him to deliver amazing value for the customers.
Thank you, Koorosh.
Fantastic. Okay, let's talk a little bit about Intellify in case you have not heard about us, you have not worked with us. We are a boutique data and machine learning consultancy. We have 3 main lines of businesses: strategic advisory, consulting and execution, as well as managed services. In the strategic advisory, which is happening a lot these days, to be honest, we work with customers on large-scale data transformation projects. We do a lot of assessments on data tooling and platforms. We do a lot of AI strategy workshops with C-levels and heads of businesses in our customers, typically enterprise customers. We have started looking into data governance as code to enable data governance to be applied at a code level at the bottom of the organization, rather than just a bunch of policies that sit in a shelf. And we have started looking into ethics frameworks for customers, because all we do here is to delight our customers, and we take the direction that the customers want us to go. We've had a bunch of really successful data strategy engagements for our customers, which we're definitely gonna run workshops around it and dissect one of these projects that we've done. There's gonna be a lot of lesson learned for you, so stay tuned. On the consulting and execution side, we do a lot of data engineering, but not your traditional data engineering of going to the Teradata's of the world and SaaS. We are predominantly focused on migrating those workloads into cloud data warehouses and data lakes. We have a very high quality team, very high bar of hiring, hence the team that we have in our data and ML engineering are the absolute heavy artillery when you engage them. We have done a number of different data migrations, a number of different machine learning pipeline end-to-end deliveries. ETL pipeline modernization is something that is a lot of organizations are actually looking into, because your typical ETL pipelines are expensive, rigid, and potentially not answering the needs of today. We do a little bit of BI, but it's not within our main focus right now. And obviously, data science and machine learning, this was how Intellify was created. This is still a core pillar for us. We solve very complex problems using machine learning and data science. We have top grade data scientists in the team that can basically make models work. We have a lot of services around forecasting and personalization, as well as optimization. So that is the consulting side. On the managed services side, we are taking cues from customers that even though there's a lot of new improvements have come to the platforms that are enabling machine learning, but still there's a huge amount of complexity to get a machine learning pipeline into production that can support hundreds of models in production, where the people running it can have a sound sleep at night. Due to reasons that I will mention in the next couple of slides, we have decided to create a bunch of services as a managed service, such as MLOps, if you dive a little bit deeper into it later in the session, or manage machine learning platform, or manage data lakes, or manage cloud data warehouses as a service. Reach out to us if any of these services would definitely deliver value to you. Our main goal, as I said, is to delight our customers. So that is Intellify. We've done projects in 5 cities in Australia, as well as Switzerland, US, and New Zealand. We have 2 offices, one in Sydney and one in Melbourne, but the majority of the team are residing in Sydney, which these days, because of COVID, it really doesn't matter because everything is virtual. Okay, the agenda for today is that, I just ran through the introductions. I'll talk about UDAP, Unified Data Analytics Platform from Databricks. And then I put myself in the shoes of an architect that is designing a machine learning platform, an end-to-end machine learning platform for an enterprise organization. I will set the scene by setting the context, telling you what this design is actually for, what type of organization, what type of team, what type of maturity. And then I'll go through all of the boxes that an end-to-end machine learning pipeline requires for a successful delivery of hundreds of models into production. And then I'll hand over to Joshi to go through the workshop. He will tell you the story of what we're trying to achieve. And then there's going to be hands-on workshops on Delta Lake and ML Flow to get amazing outcomes. And then I'll wrap up a little bit of a teaser about the upcoming data engineering focused and data focused marketing events and webinars and workshops. And then we definitely would love to answer your questions. During the meeting, if you have any questions, please pop them into the chat. And depending on how we are tracking with the time, I'll try to answer your questions. Otherwise, we'll leave it at the end. Again, if it's not possible, we will definitely get back to you after the meeting. Fantastic. Let's get started. So, machine learning is difficult, right? Machine learning is not easy. It is easy to hire a data scientist and put her in front of a Jupyter notebook, and she plays with some data, does some data engineering, comes up with a model, and the model is fine. But for people who have done this in enterprise, they know that is just one small, tiny part of what it takes to actually to take machine learning models into production. Well, we are going to look at Unified Data Analytics Platform briefly. So what is UDAP? Is pretty much the one platform for all type of story from Databricks. There's a lot of good content out there that you can watch around UDAP. It is basically built on three main pillars: an enterprise cloud service, either AWS or Azure, which takes care of your cloud governance, your security, and the guardrails you need to run your workloads. So there's tight integration between the Databricks platform as well as these two clouds that are mentioned here. And then the Unified Data Service, which is composed of Delta Lake as your data lake engine, which Joshi definitely talked into a lot more detail, as well as Spark Runtime, which can handle a number of different tasks. As you probably know, Spark is a family of different awesome tools that are available to you to pretty much do anything with the data, from ingestion to transformations to store. Everything is possible within the Spark ecosystem. And on top, to realize the value out of the data, MLflow is an open source platform which enables data science and machine learning teams to work closely with DevOps teams to develop models in a much more meaningful, much more collaborative way, and to track their experiments, to create a life cycle for their models, which makes you a lot closer to that utopian world of having models in production without losing sleep. And then there's a lot of integrations into a lot of awesome BI tools out there, your typical, your usual suspect, the Tableau, the Clicks, the Lookers, that you can access your data from those BI tools directly from your Delta tables and Delta Lake. Okay. Let's talk about, as I said, there's going to be a heavier focus on machine learning, right? And let's go through the the ages of machine learning in the past, let's say 10 years. Starting with the Stone Age, where data scientists, back in 80s and 90s and probably even early 2000s, they compiled algorithms in C++. That is not relevant now. It is not happening now. We have seen a lot of amazing improvement that has happened in the last, especially in the last 5 or 6 years. And then we basically hit the notebook age, where you jam everything into one notebook, and then when you're done as a data scientist, you throw it over the fence for someone else to productionize it, which is not a very scalable way. Maybe it works for 1 or 2 models. Mostly, the outcome of that is pretty much a proof of concept. In that time, still SAS and R are dominant languages and dominant platforms. Python is picking up pace, obviously, but still, the concept of production is pretty much a strange concept to a lot of data scientists. And then, hit 2015 to 2018, we had the platform age, where a lot of awesome platforms were created out of initiatives like Michelangelo in Uber or Zipline in Airbnb. A lot of awesome platforms were created, such as SageMaker, MLflow, Kubeflow, which streamlined the process of machine learning. Still, even with those platforms in those early days, we didn't see a lot in production, because productionizing machine learning, yes, there's definitely some technical aspects to it, but then again, it needs a lot of business transformation and cultural change as well. So it was not a simple scenario of, now I have a tool, now I have SageMaker, I have MLflow, and everything is going to go nuts. Since 2008, definitely 2018, up until now, we have seen a big shift, right? We are seeing at least the early adopters and the avant-garde type of organizations have started pushing models into productions in a meaningful way. Forget about the tech giants. We're not talking about the Ubers and Airbnbs and Amazons and Facebooks of the world. We're talking about, you know, mainstream commercial, especially with the lens of Australia and New Zealand. So in this ecosystem era time, we saw that there's a massive focus shift from doing data science into enabling the data scientists to do data engineering. And now, as you can see, if you've been hiring data engineers in the market, you know it's a very, very limited talent pool out there, and pretty much data engineers are the gold right now. This is where we are now. Tools like MLflow and ecosystem that surrounds them with all of the amazing tools that are popping out every day, from ingestion tools all the way to processing, storing, and then pushing inference. We are in that stage right now. Where we think it's going to head 2021 and onwards is going to be product thinking age. Rather than creating pipelines, we create products. Rather than doing projects, we develop products. And a big enabler of that is a paradigm shift that is happening right in the market, where ThoughtWorks have named it as data mesh. I'll get back to that at the end of the presentation, but it's basically, think about it as, you know, what microservices did for development world a few years ago. Data mesh is trying to do that with enterprise data. So that is a little bit of a brief history of what we've seen in the market in the past, you know, 10 or so years. But let's look at why machine learning is difficult, actually. There's a few reasons. Let's go through them. Number one, organizational issues. No customer I have seen that said, we have the perfect team, everyone is ready to go, everyone is working in cross-functional teams, and everyone is aligned to one goal, to put stuff into production, to put models into production. There's definitely politics always involved, especially in organizations that you know, there are different executives not wanting to miss out on this wave of data and data modernization. And then we are dealing in a lot of enterprises with silos, where IT teams are not working with lines of businesses. Usually, this is where the data scientists are sitting, and these silos are the main problem. And also the leadership around data. We have seen you know, organizations basically putting leaders in place who were not really aligned to the strategy goals of an organization. So organizational issues and company culture plays a massive role why your models are not into production. I wish I could see your nodding heads, but I'm sure a lot of people in this webinar are agreeing with me on that one. Another one is big bang approaches. We've seen a number of enterprise customers, especially the cash-rich ones, especially the top end of town, that they've started massive platform builds, and they thought that they will build it and they will come. They built it, they didn't come, right? Because it lacked the support and the buy-in from those lines of businesses, right? And ended up, you know, writing that investment as sunk cost for that. Another big problem was that in the early days of doing machine learning and data lakes, we saw a lot of this type of movement that, hey, I have a tool I have read somewhere in a website, or I talked to a vendor, and that tool is going to solve all of my problems. It is not as easy as that, as you can attest to that. There's my maps. Awesome. Okay. So the next one is that potentially another reason that your models are not in production is that IT probably is not there yet. Maybe they are just building up their cloud capability. Maybe they are very new to the DevOps concept. In a lot of cases, we've seen that the typical IT organizations, except, you know, from, you know, different pockets in the IT organization, they fully do not understand the machine learning process. They are used to running and keeping alive business applications and core systems that are very critical to the business. However, the world of undeterministic nature of machine learning is a strange concept to them. So it will take time for them to adjust. Also, on the same note, the ML teams do not understand the engineering process. They think they create a notebook with a model and it can get productionized like magically. So they have poor engineering practices. There are a lot of, well, there are data scientists in the market with poor coding skills. And you know, as I said, they jam everything into one notebook and they really do not consider what happens when the data is being ingested and what happens after the inference data is coming in. They basically say, it worked in my notebook, why can't you put it into production? Another reason for that is poor access to data, and that is pretty critical, especially in the top end of town. Data is everywhere and pretty much nowhere. They have to wait months to get access to a certain data sets, to pass through all of the security hoops, and the security teams vetoes them on many different access levels and whatnot. So access to data is a big, big issue. And also the people who are gonna, at the end of the day, sign off on these models to go to production to do something, especially if it is, you know, customer-facing decision that these models are making. There's a lack of trust in the data that is captured, or in the models, in their accuracy and whatnot. A lot of it is relating back to the poor quality of the data, and also no mechanisms has been introduced in that machine learning pipeline to detect machine learning issues such as model drift or data drift. And always, you know, when you involve the legal teams with machine learning process, they are very worried, and rightfully very worried, about bias and ethics and regulations, because there has been so much negativity in the news around machine learning and AI. And at the end, well, not at the end, one more to go, but evolution of the data market. Every day there is something new. Every day there's a new buzzword. Every day there is a new vendor saying that my platform is superior. You get choice fatigue. It takes you months, in some cases even more, to create a tender process that actually is mapping to your requirements, and then you get flooded by a lot of consulting companies and a lot of vendors out there saying that my product can do it better, my service can do it better. So this rapid evolution is also creating a lot of blockers for basically putting models into production. Another discussion that we have, especially with the top end of town, you know, should we choose cloud agnostic tools, or should we go multi-cloud? Should we stick with one cloud? Yeah, these conversations are never ending. And at the end, the legacy. You know, we're dealing with a massive amount of legacy. When you dig deep into the different generations of data warehouses that has been put inside an enterprise, you see things that only makes you laugh. The ETL pipelines, the data warehouses. It's just not going to scale for the needs of today, and especially tomorrow for advanced analytics and machine learning, right? The enterprise data warehouses are too expensive to run for you know, simple exploration and EDA type of work. I always use this this analogy that these data warehouses are like a Ferrari. They do their, you know, operation job really, really well, but you really can't take them for a grocery run. And some of, you know, these machine learning initiatives are pretty much equal to those grocery runs. You have to do it, and you have to explore. And out of the 10 initiatives that you might have, 6 of them might fail, 2 of them might be okay, but probably there are 2 that's gonna give you the jackpot. But these enterprise and these legacy data systems are not really designed for this type of work. I'm pretty sure you can add another 10 items into this list. This is, you know, our observations in the last few years of working in the machine learning side of things. But I'm sure there are a lot of other reasons in your organizations that why ML is not in production at an enterprise grade level. Let's look at a platform that solves some of the problems that we have mentioned before. Obviously, you know, cultural shifts and paradigm shifts inside the organizations and creating cross-functional teams, getting everyone to play nice with each other is out of the control or jurisdiction of any tool out there. Tools could be enablers, but that shift needs to come from another place. But enabling MLOps will enable you to quickly prove the value, and nothing speaks louder than a quick win. So I'm going to take you through an architecture. This is not the best architecture. This is an architecture of a machine learning pipeline, an end-to-end machine learning pipeline, and then we dissect it, you know, box by box, component by component. Yeah. Okay. First, like any other, you know, technical platform, you need the supporting infrastructure. The supporting infrastructure should be built on strong foundations. For example, in this case, we are using AWS cloud infrastructure. It needs to have proper security and governance and controls as guardrails for your data, for the people, for access management, encryption, and so on and so forth. Obviously, it needs a CI/CD pipeline. If your machine learning processes are not embedded into a CI/CD, a proper CI/CD pipeline, you are setting yourself up for failure. You are creating a spaghetti mesh of an environment which is going to be extremely difficult to untangle in a year's time. And at the end, it needs an event engine that can pass messages between these different components that I will show you one by one, and a job orchestrator, because there's going to be a lot of movements, a lot of different things to be called within a simple training run or a simple inference endpoint deployment. So these are the supporting infrastructure. And the next box is going to be around data, right? Data is the most important pillar for machine learning pipelines. Unfortunately, and you are probably nodding, but unfortunately, we have seen in a lot of organizations that machine learning teams did not get enough love from the data teams or from the IT teams who control the data. And they said, yeah, we're going to build our machine learning pipeline and we will work with whatever data that is available to us. This simply is not going to work. You have to consider data pipelines and data ingestion and storage and data lakes part of your machine learning pipeline. And then we have a modeling environment where this is your data scientists and ML developers and data engineers window into the platform, right? This is where you develop models. This is where you track your experiments. You do your feature engineering and so on and so forth. When you are done with developing your models, you need to push them into production. This is where you serve your models into production as live inference endpoints or, you know, batch jobs. And then you monitor the health of the model. But still, your models, the money that you have put into this platform, the money that you have put into hiring those amazing data scientists and data engineers are not giving you any value just yet until you have this layer, the integration engine, or I call it API hub, right? This is where your inference, the amazing output of these models are going to be pushed to downstream and upstream business systems. That is pretty much, and also BI reporting. Usually BI is not being included in the machine learning pipeline because, you know, it deals with different types of data and different types of requirements. But it is good to have a BI environment available to those data engineers and data scientists, and we will cover the reasons as to why. So these are the big building blocks of this architecture pipeline. We're going to have a lot of different little boxes in each of these that I'm going to go through quickly and give you some tips and tricks that we have learned over the years of deploying these ML pipelines. But first, let's give you some context, because this pipeline that you saw is not a one-size-fits-all. You cannot deploy this in a company like Atlassian, also deployed in Commonwealth Bank, also deployed in a small startup with 2 data scientists. So this comes from a certain type of principles and requirements. Let's go through them quickly. First, it is designed for enterprises, right? If you are an enterprise who doesn't have a large data or machine learning team, probably you're over engineering and overspending on building such a platform. This is designed to handle thousands of models in production, tens of petabytes of data. So this is definitely designed for scale. It doesn't mean that if you have one model, it's not going to work. It's absolutely going to work. But this is designed to scale to levels that can actually generate tremendous value for your business. It enables rapid innovation and also enables you to fail fast. It requires a bit of upfront engineering, but the efficiency that you'll get out of this platform is amazing. It's designed for low OpEx. CapEx is a different story. As I said, these type of platforms where you are hacking a bunch of services together, creating pipelines, run them as a product with proper roadmaps require a little bit of upfront investment, right? But it is designed to run on a pay-as-you-go model on cloud services, mostly serverless, where you only pay as you use, and this is definitely going to bring a lot of value. But we know that within the last 4 or 5 years of working with cloud and working in the cloud, a lot of companies are not prepared to adopt an OpEx model because they are still looking at massive refreshment cycles and stuff like that. So there's going to be a lot of shifting in that regard. And the platform is secured by design. Rather than retrofitting security controls into a platform, it is designed for every single component that I will go through in the next few slides. This is based on a cloud data lake, this architecture, but you can replace that with your own flavor of data lake, your own flavor of cloud data warehouse. We definitely do not recommend you to do this on premises on your rigid rigid infrastructure, but definitely this is based on a cloud data lake. And also it is designed for high reliability. Yeah, having models in production is one thing, ensuring that today it is providing the same results, or not the same because these are stochastic type of models, but an acceptable result today as tomorrow, as 6 months from now, as a year from now, is actually a lot of work. So this platform takes care of that reliability. Okay, remember, this was the context for the next few slides, but these are a couple of important points. A good architecture is the sum average of all trade-offs. You don't have unlimited cash, you don't have unlimited engineering resources, you don't have sometimes buying from top execs from the in the company, you don't have a proper cloud team. So there are a lot of trade-off goes into deciding what architecture best suits you, right? So a good architecture is the sum average of all trade-offs. And also, a good architecture is a trajectory, not a destination. Start small, iterate fast. You don't need to build the entire platform that I'm going to show you in one big bang. In fact, that is the wrong way of doing it. So start, have a target state in mind based on your needs, your requirements, where you think your organization is going, and then start small. Okay, let's get started. As you can see, I'm going through these boxes one by one. We're talking about the foundation. This is where your landing zone is. This is where you land in the cloud. If you have already adopted cloud, you already have an infrastructure that is taking care of your single sign-on, that is configured to work with your on-premises networking, with your offices networking. You have your VPC set up, and all of the good things that come with the cloud. This is not the focus of this discussion, but I guess if you don't have that type of readiness to go into cloud, you definitely need to consider one going forward for this architecture. And then security and governance. This is where you, as a central command, you apply your governance, your security controls onto the entire environment. Most of it, if you're already in the cloud, most of it is already built for you. Most of it is already integrated into your identity providers like Active Directory and whatnot. But there are certain data-specific configurations and security controls needed to enable your data to be stored securely. For example, we're going to talk about Databricks Delta. With Delta, you have granular security controls you can apply, like access control. Integrating that with your cloud infrastructure and eventually with your identity provider, which in majority of cases is Active Directory, is going to be extremely important. I will share this deck at the end, well, next week with you, and I'll put a lot of links as much as I can into the deck, so you have more resources to go and look through these stuff that I'm going to go run through very quickly. And then a CI/CD pipeline. As I said, no point for thinking about production if you don't have a CI/CD pipeline. There are just too many moving pieces that is going to hurt you very quickly after you productionize a model if you're not using a proper continuous integration, continuous deployment framework. There are a lot of tools out there. It is a very mature market. You're already using it. The Jenkins of the world, the GitHubs, the GitLabs, and infrastructure as code, your typical CloudFormation or Terraform. Think of this entire platform that you see on the screen as a product itself. Right? It needs to run as a product. It needs to have a roadmap. It needs to have infrastructure as code. The entire platform is actually a code in GitHub. So I cannot insist enough on the importance of having a CI/CD pipeline. And at the end, you know, your usual suspects when it comes to job orchestration and workflow management. In this example, we are using Airflow, but these workflow managers are growing like mushroom these days everywhere. Every couple of days, I see a new startup having their own little niche with Airflow. With job orchestrators. We don't recommend which one to use. There's definitely a lot of them out there. If you want to build something completely native to AWS, Step Functions is a good one. If you want to take your job orchestrations out of the tools and run it externally, Airflow, Apache Airflow is a good one. What we recommend is that to stick to one workflow orchestrators because it's going to create complexity. Another one is to create repeatable DAGs, create repeatable workflows that could be used across the organization by different teams and catalog them and evangelize them, right? Hey, we have created this pipeline. It is running exactly like this. Why don't you use the DAG that I created before? And also, do not overthink which solution to use. Make it modular, make two-way door decisions in case you need to change it 2 years from now, because the needs of the market are so rapidly evolving that, to be honest, I can't tell you which one of these platforms are going to be winner in terms of where machine learning is or where data is going. Okay, the next set of boxes are the data layer and our feature store, right? It is important. Yeah, the title is there. It is your job. If you are a data scientist, if you are a data engineer, if you are a machine learning engineer working with data scientists, yes, it is part of your job's requirement to think about running a sound data platform. So build it with repeatable and reusable ETL patterns. Acknowledge there are different types of data, so be prepared for that. We will go through these, data transport and ingestion mechanisms later, and then remember that the true north is the TCO, not the cost of the platform. Yes, when you look at some solutions, they might seem expensive, but when you are looking at the efficiency that you'll get out of them, make sure that you do not fall into the trap of procurement processes that look into a platform cost. The true north should be your TCO. How many data scientists you're going to put into this platform, how much efficiency you can give them, how many data engineers you need, how much efficiency you can give them. And I personally, and Intellify, definitely we try to stick to open source technology as much as possible because of many, many reasons. Probably all the good things about open source technologies, right? And also feature stores. I'm going to cover feature stores in more detail, but it might be a fancy word for you right now, but trust me, you're going to need it when you have more than 10 models in production and when you have more than 4 people in your data science teams. And also make sure the data is discoverable and addressable. Do not build another copy, another replica of what you are calling a dinosaur legacy. Apply new concepts to what you're building, making sure your data is discoverable, is addressable, is interoperable, which we will cover in the final slide of this presentation. Let's go through the boxes though. So in the data layer, we have a data ingestion, or I call it the data transport layer. Acknowledge different types of data. You have streaming data, you have micro batch data, and you have batch extraction and load methods. Build modular and loosely coupled ingestion layer solutions. For example, don't think that a tool can serve every different types of data ingestion. You might use Apache Spark streaming for certain type of IoT data ingestion. You might use Kinesis, or you might use Fivetran because you have a lot of SQL databases or a lot of other SaaS applications that you need to ingest data from. So go really modular as much as you can. It also allows you to forklift change that specific solution with something else without the need to change the entire pipeline. Excuse me. And minimize data duplication. This is extremely important because there has been a lot of ingestion tools out there in the market that are low quality and create duplicate data. And if I had a penny every time you told me that so-and-so solution falls over and does not handle failures gracefully, and then we come in the morning and a bunch of data that was supposed to be ingested is not there, so everyone is basically twiddling their thumb, not being able to do any work because the data was not ingested last night. So select solutions that can be that can handle failures, and also integrate data unit testing and expectations check early on in your pipeline, because if you don't capture it in the transport layer, it's going to corrupt the entire data flow within your pipeline and potentially find its way to here, where you are serving your models, which is going to be very bad outcome for your organization. When it comes to Data Lake, Josh is going to take you through Delta. Data Lake has evolved over the last 5 years. When I joined Amazon, it was the whole buzz around data lakes and serverless data lakes. In reality, it was an object store that could handle a lot of files, a lot of objects, and then eventually it started, building solutions on top of S3 that enabled people to query the data sitting in S3 as a very inexpensive way of storing data. But the needs are growing. Data lakes are getting more important. Data warehouses are pumping stuff into the data lakes, and we need newer tools. That's why we personally, like in Intellify, we love Delta Lake as a product. It gives you ACID functionality if there are multiple users trying to read and write from the same objects. It basically abstracts what is an object store and gives you that data warehousey feel, right? And it enforces a schema structure early in the pipeline. So if you're not expecting a certain column to be there, it basically drops that write request, and it enables you to do schema evolution. These are very important factors that you don't get out of a simple object store. And it accommodates data versioning, or as Databricks Delta calls it, time travel. So important. What an important feature, this time travel. This is one of the major concepts within data mesh, to be able to version data and reproduce a certain BI dashboard, or reproduce a certain model based on data that we had, let's say, 3 weeks ago, which you'll get out of the box without implementing very painful ETL pipelines just out of the box on Delta. And Select a solution that can handle batch and streaming data without extensive engineering efforts. And that Delta Lake provides you with that. Not going to dive too deep into Delta. Excuse me. And then we have the ETL and feature calculation. Spark Runtime is a perfect tool for that. I'm not going to spend too much time. Joshi will show you there. One thing that I would love to dig deeper here is feature store. If you're a data scientist, if you have done a little bit of machine learning before, you know what features are. Features are the building blocks of what we are feeding the models, the algorithm to create a model, right? A feature store was a concept that was introduced by Uber back in 2017, and it has been dubbed like feature engineering is the hardest part of doing machine learning, right? And it is the most time-consuming part of machine learning for data scientists, and a feature store is a central repository for all of these curated features. It gives you a lot of awesome capabilities. First, it creates a consistent pattern to reuse features. So if you are coming up with a certain feature set for a certain model, then you can extract that feature pipeline, put it into your inference pipeline, and come up with the same data that is going to feed your inference pipeline. If you don't have a feature store, there's going to be a lot of engineering involved to make sure your data scientists are producing proper ETL codes to feed your inference pipelines as well. Another one is feature reuse across different pipelines. Yeah, you might create a feature group that has certain attributes, and you can easily excuse me, just gonna move this one here, and it can easily be reused in other pipelines. So it's gonna save your data scientists and your ML engineers and ML developers a lot of time. It removes the duplicate feature engineering work. As I said, different data scientists can create feature sets, advertise them, put them in the feature store, and search for them. So, you know, different teams do not need to waste time every time they are starting a simple model. And one thing that is really important is that when you get a new data set for the same model, you have to calculate all of your features and all of your data one more time. This is putting a lot of cost into these ETL pipelines or transformation jobs to run, where a feature store enables you to get rid of that, only calculate the features that are new that you need to fit your models. Yeah, well, that is a duplicate there. I'm sorry about that. And then your data store needs to have a feature repository where your final training and tests and validation sets are residing there, cataloged and indexed, where it's getting fed into the machine learning pipelines. And now we're talking about the modeling environment. This is where things get interesting for data scientists, data engineers, and ML engineers. The tagline up there is think like a data scientist, but develop like an engineer, right? This is the biggest gain you can get out of any data science teams, to get them start adopting software development best practices. It starts from this layer. It starts from this modeling environment. So the runtime, or as Databricks, in the Databricks lingo, they call it the workspace, is going to be extremely important for your data scientists to come to their work every morning, log onto their workspace, and have the same type of packages and libraries and environments ready there for them. Another big point here is to track your experiment. Those days of one data scientist being a lone cowboy and, you know, everything is basically sitting in her head and not being, you know, stored other than maybe a couple of comments in a notebook are long gone. Track your experiments, track the data sets you use, track the notebook version, track the code you use, and obviously track the metrics of your models into a central tracking repository. We will go into more details later. And there is no point doing in model tuning and hyperparameter optimization these days yourself as data scientists. There are a lot of amazing work has been done to automate that. So take the human out of the loop for HPO and let the machines find the best features and for the data in and hyperparameters for your models. And at the end, model lifecycle management. Models, you create them. If you don't put them through a very robust and strict lifecycle management, you'll end up with an environment you simply cannot manage. Let's go through these boxes quickly. The MLflow workspace will give you access to a really nice collaborative notebook environment. Not a lot of time to go through that, but Joshi will show you. ML runtime will enable you to create a repeatable package runtime with all of your libraries and packages and frameworks and notebook versions and tools and Python versions, everything packaged together, ready to go, so you can reproduce your work every time. And also, it is extremely important to move away from notebooks as the source of truth to Git as the only source of truth, right? There's a lot of improvements coming into MLflow workspace based on the new feature that they announced in Spark Summit a couple of months back called Workspace 2.0, which has great integration into GitHub and so on and so forth. And then at the end, enable collaboration. Collaboration starts with a nice tool that enables these data scientists to share insights with each other, to share notebooks, or to share snippets of code with each other, and to allow them to work collaboratively on one notebook or one initiative, right? So going to the modeling and EDA or exploratory data analysis phase. This is where you do a lot of modeling. This is where you come up with new features. And when you see something might has legs, you run your trainings, and then you track that experiment using MLflow tracking feature. It is extremely crucial for you to track everything with that training job, like the data you use, the location of the data you use, the model parameters, the notebook version. So basically pretty much tag everything that you can and send it to the tracking for reproducibility down the line. When it comes to packages, one really nice feature and concept from MLflow is MLflow models, where you basically produce your model once and then you can deploy it into different flavors. For example, you can create a flavor for, hey, this model is going to be deployed in a Python environment, or this model is going to be a TensorFlow environment. This model is going to be a scikit-learn or an XGBoost. This concept of flavors, again, saves a lot of time for your ML engineering and even data scientist team to run experiments and deploy models into production. As I said, HPO, hyperparameter optimization, is something that is pretty much being done, if not on par with humans, very close to it, but a lot faster, With hyperparameter optimization, you can use, for example, MLflow's HyperOpt integration, where Spark will create a bunch of machines under the hood, run many different training jobs at the same time with different hyperparameters within the ranges that you define, and then gives you the best hyperparameters to train your model with. Joshi will cover that in his section. And at the end, the model registry. This is everything. Right. When you have a model could be in different stages. It could be sent to a staging environment for UAT testing. It could be actually in production, or it could be decommissioned and now needs to be archived. So in model registry, you can go into that UI and see your model and track back all the way to the experiment, track back all the way to the data that was used, track back all the way to the code that was used to build this model, all the graphs and all of the metrics that you've tracked with it. And that model is the single source of truth that needs to be deployed into production. When you transition a model through a stage, which could be a workflow that you design that, for example, my data science team come up with a new model, that model needs to be approved by a data science manager. Data science manager look at the model, look at the metrics. No, it's good. Push it into staging. It goes into staging, and these tags can be used by your CI/CD pipelines to take the model and push it into a deployment environment in UAT or in production, or put it into an A/B testing setup, or put it into a blue-green type of deployment. So there's a lot in that model registry, which makes your life a lot easier. And also at the end, the batch inference. Usually I put inference in this section, anything with inference, including batch. But I specifically put it here because there's a really nice batch inference capability right out of MLflow, where you can run Spark UDF basically to run your inference jobs. And I have included in this section in the modeling environment, but in reality, inference logically belongs to the model serving. Don't worry about this. I'll definitely send you this. These are some really, in my opinion, and I have to be humble, but really good information based on the battle scars we had in so many different projects and working with so many different customers. Let's talk about the model serving environment. Specifically, we're talking about live endpoints, the model that need to sit in production and produce, basically answer to an inference call and produce a prediction or a forecast, or generally an inference. We highly recommend you, for that type of setup, use a cloud inference service. For example, SageMaker, right? SageMaker is a good inference service. Obviously, we are an Amazon partner, so we have a little bit of bias, but SageMaker is definitely an amazing tool to deploy your models into production. Make sure that part of that workflow where you're handling the models from the development environment into your model serving environment, there are provisions for model monitoring, specifically drift monitoring. I will cover that in a little bit more detail. And also make sure that you are using all of the best practices that we have learned over the years of managing production environments in the dev world. You're using that in the model serving environment as well, like blue-green type deployments, like A/B testing. Let's look at these boxes in a little bit more detail. Starting with live inference. So the CI/CD pipelines are tagging a certain model to be deployed into, let's say, a staging environment or into a production environment, and they pick the model with some bit of code that you can develop and push that into SageMaker. However, there's a really, really nice integration that Databricks has created, where you can create a model flavor for Python, and there's a bit of a simple integration that can pushes your model directly into SageMaker. In many, many cases, that is more than enough. However, you might want to take that logic outside of that bit of integration that MLflow has created, and deploy it on your CI/CD pipeline. For example, I'll get to that when I explain A/B testing. Yeah, the inference endpoints in SageMaker, they can handle scale automatically. They can go up and down as needed based on the number of connections that they are getting and based on CPU usage and stuff like that. However, like any other load balancing scenario, be careful with surges and sudden spikes. So if you have a recommendation engine and it is, you know, a specific day that your organization is, you know, doing massive offers and everyone's going to come in, pre-warn your SageMaker endpoints. Another important factor, probably one of my favorites and one of the most important ones, is drift monitoring. Models can drift because of two main reasons: a gradual model drift, which can happen. Basically, a model is there to change the behavior of a target system. For example, a recommendation system tells me that people who have bought this also bought this, so my behavior will change. Instead of buying one, wipe to. After a while, there's new data. I shift my behavior. I will create new data for the systems, and the old data that was used to train the model is no longer relevant. That is one gradual way of models drifting. Another one is a sudden change in the inference data. We had scenarios, for example, in an energy company where the regulators forced them to do some pricing changes, and we built them a dynamic pricing model, and suddenly models were completely out of whack in production, producing garbage inference. If you don't have a process to capture those type of events, your data scientists are spending all of their time in troubleshooting rather than modeling and creating new initiatives and testing and prototyping and coming up with ideas and chasing hypotheses. All they do day in, day out is just doing troubleshooting of your models. Model drift in SageMaker has a very, very strong, awesome capability called SageMaker Model Monitor, which is a flavor of Apache DQ. Apache DQ is a framework that is being used for data unit testing. It takes a baseline of your training data and then run a statistical analysis of the baseline data. And on the schedules, it comes up, checks your inference data, compares them, and see if there's a massive drift being detected. Then it can trigger something like an alarm or a notification, which can also, you can embed it into your CI/CD pipeline to, I don't know, trigger a retraining, for example, in different cases. A/B testing is also another awesome point here. Apologies. A/B testing is also another awesome feature of SageMaker inference endpoints, where you can develop multiple models, put them into A/B testing setup, and redirect a certain percentage of traffic to each of these models. For example, I have a model which is receiving 90% of my traffic, and I have another 2 models receiving 5% each, because these 3 models are being developed using the same data, but with different hyperparameters, or even different algorithms, or different even different data. So A/B testing or ABC testing will enable you to implement that out of the box in SageMaker. However, there are scenarios where you want to take your A/B testing logic outside of SageMaker and put it in front of SageMaker, let's say in a load balancer or in an API. This is for really complex situations. For example, if you are doing blue-green deployment with A/B testing of models, probably it makes sense to have a look at the limitations of A/B testing feature of SageMaker, and maybe take that traffic routing logic out of SageMaker and put it into a layer in front of SageMaker. Another good feature, well, it is not a feature of SageMaker per se, but you can definitely deploy it with your CI/CD pipeline, is blue-green deployment. If you're not familiar with blue-green deployments, blue is the model that is serving the traffic right now. You have a new model, you want to replace it, but you don't want to do a sudden basically replacement. What you do is to bring the new model in a green environment, and then either gradually or suddenly switch the traffic to the green environment. Green becomes the new blue, and blue will basically stays there for a number of days or a number of weeks in case we are sure that this one is producing the good results, and then you can decommission the blue environment, the old blue environment. You can definitely implement that in CI/CD pipelines. Yeah, a lot of IP around that, whether you're using Jenkins or whatever your CI tool or CD tool is. There's a lot of good IP around that. And at the end, as I said, it is extremely important to push those amazing inferences that your models are producing to your downstream systems, typically your ERPs and your CRMs, your core business apps, or simply your digital assets like your e-store, etc. For that, we have provisioned in the IP that we have at Intellify. We have provisioned for an API hub think of it as a catalog, as a developer marketplace, think of it, where you can easily pull certain API out and say, hey, I need an API that creates a CSV file or creates an Excel file with some graphics and whatnot based on the results of my inference, and push it to the actuarial team, for example. Or it could be more complex APIs. So in this layer, you typically have the APIs that you will build in-house as integration layers. It can have data extract and load tools like, you know, Fivetran or Appflow, reading data of a Delta table or an S3 table and pushing it into other systems. It could be real-time streaming systems where you basically push the results of a log inference into a, let's say, a Kafka a stream or a Kinesis stream. It could be a simple enterprise message bus, like your MuleSoft environments and whatnot. It could be an SFTP server generating a file out of the inference and then, you know, push it into those old dinosaurs out there who still use SFTP, etc. And at the end, the BI and reporting layer. As I said, you know, BI usually doesn't sit in this environment. It is being handled usually by other teams in the organizations that we work with. But it's good if you have some BI capability, whether a cheaper version of, you know, what Tableau is, or if you have a lot of Tableau licenses, to include Tableau here so your data scientists and data engineers can hook into your Delta tables and read off your silver or gold tables that you create and generate some insights, because what they do in the EDA phase can actually produce some amazing gold nuggets, as we have seen the work that we've done at Intellify. Yeah, that is it. So I hope this was aligned to what you were expecting out of this, and I hope it wasn't too technical or it wasn't too dumbed down. I know we have a wide range of audience and we have to cater for different personas here, but I would love to run this in more detail or in less detail, however you would like it, for your organization. So please reach out. Excellent. I'll hand over to Joshi to start his amazing section. Joshi, that's a loss.
Thank you, Koorosh. So for this demo, what we're going to go through is take you through the end-to-end workflow for the predictive maintenance for a wind turbines. So how we're going to do that, we're going to splitting this demo into two sections. So first of all, we're going to collect the data from the wind turbine as the sensor readings around different gearboxes within the machine. And then we're going to load the data into Delta Lake, explore the data a little bit and try to see if there are anything we can find over there. And if there are anything in the data, we can try to visualize the data and fix the issues within the data, and also trying to optimize the query performance. And once we have a good data quality within our Delta table, we then go ahead and create a particular classifier on top of our data, and then trying to predict the failures of your wind turbines based on the sensor data itself. And then to work out the best model, we're going to use the HyperOpt as a tool to do the hyperparameter tuning. And then we're going to go through the ML flow with a Apache Spark model to find out the best model around that. And then using that best model from the ML flow to actually give you the real-time predictions by deploying this particular thing into a Spark streaming app we're going to build. So before we go into the notebook or the coding side of things, let's talk about a little thing about Delta Lake. So to recap a few challenges with the Data Lake, Koorosh mentioned already, is some Spark job. When you run Spark job against a S3 or other Data Lake storages, sometimes the job might fail. And when the failed job is failed, it actually trying to or maybe leave a trace of corrupted states and with some uncleaned jobs, uncleaned files within them. So it's quite difficult to recover from that particular stage, because normally people just delete all the data for that failed job and then rerun the entire workflow again. And then the next thing about the challenges in the data reliability is the lack of schema enforcement. You can literally write any data into any partitions in the S3 path, and then it won't be any issue. But when you're trying to read the particular partition as with other partitions as well, you're probably getting some issues like schema mismatch in Spark or something similar to that. And also lack of consistencies, since you can't really read the data while a writing job is actually writing into the table in your data lake, since you might read the data differently during the period of writing. And also some performance challenges within Spark and writing data into data lake directly is sometimes you might experiencing with the packet writer or CSV writer in Spark job writing too many small files or even some very big files. So this will be resulting the job itself trying to opening and closing the file a lot rather than just reading, rather than just spending time or more time reading its content. And also partitioning. So there isn't a technical indexing concept within data lake. It's more to partition your data. So to partition your data, you will have to choose a specific column to be partitioned down. And if you do pick the wrong field, which can lead to many dimensions or many small partitions within the data, which can lead to the similar problem you have, which is too many small files. And also caching. So cloud storage can be a bottleneck of the overall throughputs because it provides much slower IOs than the normal SSD. And with all these challenges, there is another state we are trying to avoid, which is data swarm. Try to think of this scenario that you have a lot of corrupted files failed, and then you fail to actually capture or track these particular jobs, and then you have left out some corrupted files in unmanaged states. And then there could be some job writing too many untracked small files, and also some partitionings. So keep repartitioning on the data, but some partitions might be left out, and then those data will be completely untracked and unmonitored by any source of tools, and that will be creating a data swarm which have many files you might not really need, might be corrupted on your data quality for further model trainings as well. So Delta Lake tackles most of the challenges we're talking about. So first of all, it actually ensures all the transactions in Delta Lake is ACID. So especially it provides the atomic writes and reads. So it gives you the consistencies. When you read a particular table, while you're writing to it, you only read the consistent data. And the write data will be only available after the write is successful. And also it provides the enforcement of the schema. What that means is when you're trying to write a delta table, if the data in your data frame is actually different from what the delta table is, it will fail this particular run. So it won't even to actually writing data into a new partition, for example. And also Delta Lake stores data snapshots of every major operations you run on your data on your delta table. It also allows you to go back in time, and then you can pick any data snapshot back in time and then trying to recover it from that state or roll back from that state. And also it provides some Delta engine functionality which can optimize your query performance. This including to actually creating your own indexing kind of functionality on top of Data Lake and Spark, and also do the data skipping by clustering similar data together in the same file, and also doing the compaction on if you have too many small files you're trying to produce you with a relatively bigger file with instead of having too many of the small files. And also it can cache a subset of the data in any delta table, and then this caching data can be used in other applications or other pipelines. So for this first part of demo, we'll be mainly focusing on 3 parts, which is reading two data sets from the sensor data of our wind turbine. We read our healthy data, healthy sensor data, and also damaged sensor. And then we're going to combine them into one delta table in Databricks notebook. And then we're going to export this data a little bit. We might find some issues like incorrect data or missing data even. And then we're going to try to fix the data by perform a upsearch merge call into the Delta Lake using Spark. And at the end, we're going to do a little bit on the optimization of the file itself to ensure the query performance is is optimized. Let's switch to the notebook itself. So a little bit about the dataset itself. We're going to use the sensor data, and then so the sensor data is located in the gearbox of the wind turbine, and then we're going to use that reading to train our random forest model, and then trying to use that model at the end to predict if this particular vibration from the wind turbine could be indicating a failure or not. So the data looks like this one from the sensors. It contains about 8 sensors around the wind turbine, and then also another column using as a speed, like how fast this turbine is working. However, in this demo, we're only going to be using the sensor data only. So recap on these steps, what we're going to go through. We're going to go through the first 3 steps in this first part of the demo. Is import the data, explore the data, and rectify the data, and optimizing the data where we can. And after that, we're going to go through the whole ML life cycle to do the training and tune your model and deploy the model. So I won't be able to go through every single line detail of the code, but for some key lines, I will try to zoom in and trying to see highlight details. But if you do want to run this code itself, we will be also including the archives of the notebook and data itself after this session. So if you're interested, you can feel free to play around with it after this. So first of all, let's set a few paths in the variables right before we actually trying to do our jobs. As we talk about, we're going to load in the damage data and also the healthy data sensor, healthy sensor data into our Delta table. Let's go ahead and run this particular thing, set up the variables, and do a little bit workspace cleanup before we actually do the job. And then we are going to importing some standard library for PySpark, which is just like a normal Spark job. And then we're going to keep going on here to read our data. In our case, this is nothing right into Delta Lake yet. So it's really just a normal Spark job reading CSV file with different limiters. And let's go ahead and run that. So once the data is reading into 2 different data frames, what we're going to do, we're going to combine them together into one union data frame with an additional column called reading type. So we have separated healthy data and damaged data and combine them into the same data frame. Now, the next part is the key part where we just write data into Delta Lake. So it's quite similar to writing a data into normal S3 or normal Azure storage. Is the only thing to change is the format. So Delta Lake is a it provides this particular additional functionalities. You can actually use in Delta as a format. So we are trying to taking care of other things and how this job will be written into your data lake. So it's quite straightforward to write into a Delta and create a Delta table. Now it's finished now, and let's go ahead and rewrite our variable to read the data from the Delta table itself. Now, up to this point, it's quite straightforward to actually load the data into Delta Lake. And then let's export the Delta table and see what actually we have just loaded. So this can be done by doing a high-level disrupt call and visualizing with the display function in Databricks. So this would tell you there's about 4 million records and some basic statistics around it. And then if you want to do a more deeper explorations on the data itself, we can sampling a few thousand, we can sample in this case 1,000 records and trying to display this in the manner of what's the correlations between different sensors. For example, we have 8 sensors, and this trying to show what are the correlations between the healthy and damaged data around different sensors or pair of sensors. Just a rough look at this. The healthy data was tend to be grouping together in the space, while the damaged ones is more tend to be spread out. So there could be scenarios that you get your data from the data ingestion team or data engineer that it can be having some issue with the data itself when you're trying to export the data to do the training. And before reaching that state, you may be able to identify some data is missing, or some data might be having wrong values, which may need to be corrected first. Because if you're using this kind of data in the machine learning life cycle to train your data, you might get a very different performance on the models as well. So for example, in our data, let's take a deeper look. There might be some missing data over here that we made over there. And on every single day, you roughly have about 86,000 records, but at the last day of the data, right here, which only have like 43,000. So there are about like half data missing on this particular day, which is 6th of February. And we will go in and look a little bit further later. And there could be some scenarios like incorrect data that you might be having inside your original or raw databases itself. In this case, what we're going to do is we're looking into a specific reading type, which is our healthy sensor reading, and then trying to see if there are any abnormal readings we can find over there. In this case, on this particular day, 31st of January, there is a very steep readings on the average sensor reading, average sensor values. So this may be indicating there could be something you need to update it, or there could be something you might need to look into further. And in our case, we have kind of find out there could be some issues with our missing data records. So we have found out there are missing records for the healthy and damaged records in 6th of February 2020, and also some incorrect readings for only the healthy records in 31st of January. And then there could be later works on top of this thing, and then it will be providing with another data set from the data team itself, and then you're trying to fix your data before you go into the training part. This part, what we're going to do, we're going to prepare our upsert data frame, just trying to do a merge call to our Delta Lake directly. So similarly to what we have done at the very beginning, we're going to load the healthy data and also the missing damaged data, and then load them into the data frame. Do the union together so we can actually write the data in from one single data frames. And then we're going to see how just a rough look on what the new data or the missing data looks like. So a rough counting on the data records. We have all the records and only the records on this particular day, which is when we have the missing data. And this is pretty much the other half of the missing data we have for the healthy and damaged data. And then for the wrong data, we're going to correct them. So we're going to prepare our updated data with the new data set. We're going to update our existing data in the Delta table. We're going to load the data quite similarly as what we did before, loading as a CSV file, trying to give a rough look on what the data will be looking like. So this indicates a rough look on the sensor vibration pattern, which looks normal. And let's do a rough count on how much data we're going to update, since we're going to update the entire day's data, and that's about 86,400 data points we're going to update. So let's go ahead and prepare our upsert data frame. So in this case, we just combine our two missing data, which is inserting only, and also our updating data frame, which is updating the existing values within the Delta table. And then we're going to combine them together, do a rough statistic on that, indicating this might be the number of records we're going to update our table. And since Delta Lake, as we talked about, enforces the schema, so it's not necessary, but it's recommended to actually verify the schema before you actually write into it between your upsert data frame and also your Delta table. In this case, to verify the data columns and also the data type itself between these two different data frames. And then once it's done, what we could do is we can go ahead and upsert our data. Just a high-level stat recap. We are going to insert 43,000 records into healthy and another 43,000 into damaged records on 6th of February, and another 86,000 records updating the healthy sensor data value only on the 31st of January. So doing upserts with Delta Lake is quite similar to do the upserts or merge call in any data warehouses. So first of all, you need to prepare a match condition, which indicating this is a condition I'm going to update my data. So if this condition is matched, if it's healthy data on this particular day at that particular time, I'm going to update it with these values. Otherwise, if the match condition is not met, I'm going to just insert the data as a new record into my Delta table. So the keyword for doing a merge call in Delta table is merge. So it takes about it takes a data frame and it takes the conditions as what we already specified and a bunch of configurations on what will be the actions when the match condition is met and what will be the match condition when it's not met. Let's go ahead and run this update. So also with this merge calls in Notebook, you will see a like a title logins kind of thing over there, and it shows you different stages for different Spark jobs you launches, and also see different timelines, different logs over that if you are interested to see the details of the work. Okay, so now the data has been updated and merged. Let's see if our data have been fixed or not. So doing a very similar record count on the reading types and dates. And this was the day we have the missing data. Right now it's being fixed, which is good. And now we're looking at if our data has been corrected on this date when we have the healthy sensor data. And the date was 31st of January right here. And now we have much normal reading as indicating that's a healthy sensor vibration. And also another feature with Delta Lake is it keeps your data snapshot, and you can query every single history you made or major updates you made to your table. In our case, we have in this point we have two different versions of our data table in Delta. One is when we created them, and the other one when we do the merge. So this is the merge call, which version 1 we kill the data, and then the merge. And then the data before we doing the merge, which is the wrong data or some missing records and incorrect values we had before. So you are having this flexibility to go back in time to actually query any data you like in the version history. For example, if you're trying to go back to the old data we had, is you can just indicating what versions of data you want to load. In our case, we're going to load the first version of data, and then everything else will be just similar loading a normal Delta table. And then this will show you the data as what we had before, which have a missing records right here on the day of, well, the last day. And also similar thing for the incorrect data ratings. So it actually keeps the data snapshots every time you're trying to do that. And also you can actually query your latest data. So by default, if you don't specify this particular line, you were trying to read the latest version. But in this case, we'll just to show the functionality of this, and we will go ahead just to see both of the data are persisted in your data storage and tracked properly with Delta Lake. Now, let's go ahead and look into a little bit details on what we have just inserted or just queued for our data set. So we have updated our data in this particular partition, which is 31st of January. And right now, this table is having about like 3 files. And similarly to this one, we can have another one, additional files over there. So when you're keeping too much histories, for example, at the moment we don't have much, but if you do have too much histories, you actually keep multiple data snapshots, which can have your data storage grow exponentially. So what we're going to do is what we are trying to do a optimization call to optimize our file stores on our data storage in the Delta Lake. And that would be pretty similar by running a SQL statement using the keyword optimize. And on this particular Delta table, we are specifying another condition to optimizing data only in these 2 partitions, because that's the partition we just updated. Let's go ahead and run this optimization. So this will work out what optimization will be doing. And then in this case, it's trying to do a little bit, outputting a little bit statistics for you. Say some files have been updated, files have been removed as well. And then this major compaction or major file updates will be also logged in your history. And then, but as we talked about, this is not really deleting your data yet because it keeps a snapshot. So how to clean up your data set is really just to do a vacuum operation. In our case, we're going to do a vacuum on our data table and deleting everything that's not being used by our latest version. For example, after we do in vacuum, we will probably see just one file over there, which is compacted and optimized, and similar thing with the other inserting missing data in our partition as well. And a key thing to point out with vacuum data or on your data table is be really careful on doing the vacuum operation, because once you do that, the deleted data is not be able to be recovered. And if you're trying to do some point in time reading your old version data like this, you probably get an error message like that indicating that your data is already deleted and not tracked anymore. So that's pretty much Delta Lake at the moment. Let's switch it back to talk about later thing about ML Flow plus HyperOpt, what we're going to use. So ML Flow is literally just an end-to-end ML lifecycle management tool that can use. And some key functionality we're going to use here are using the ML Flow model runtimes, including different frameworks like XGBoost, TensorFlow, Spark Streaming, Spark ML, and other tools. In this case, we're going to using Spark ML to do our jobs. And also, we're going to using ML tracking functionality to track all the parameters we put it through for the model training, how the model is performing by logging its metrics, what are my historical or past run model artifacts, and what are the metadata around that. And once the model is trained, we can put this into a model registry, and then can be consumed by other applications like a Docker app, Spark Streaming, and even some third-party cloud services. So when talk about a little bit, into the HyperOpt is ML Flow provides you the tracking functionality, but it doesn't really give you the ability to select the best ones. So what we're going to do, we're going to use in the tracking functionality in conjunction with HyperOpt to do a hyperparameter tuning in distributed way, which is in our Spark cluster. A little bit high-level view about what HyperOpt is. It's a Python package which is integrated with ML Flow seamlessly and provides you various algorithms to the search spaces. As what Koorosh mentioned earlier, we'll be using the Bayesian approach to do the hyperparameter tuning for the space search, and they also provide you other functionalities and flexibilities on specifying different requirements for the search spaces on different hyperparameters. So we're going to tackle these last three steps over here, which is we're going to go ahead and create a classifier using Spark ML and then track them into ML Flow. And then we're going to use the HyperOpt to find out what the best model is by doing multiple runs or multiple iterations of hyperparameter tuning. And then we're going to score this particular vibration based on what the model output is in the real time in Spark Streaming app. Let's go ahead and go back to the notebook and go ahead and do that. So first of all, we're going to load our data from Delta, which is our fixing data, which is up to date, fixed, and in good quality. Then we're going to create our first model in random forest using Spark. However, before we actually doing the training itself, we're going to using Spark ML pipeline to do a little bit about the data processing, like vectorizing the data, normalizing the data on the continuous values, and then also trying to converting the categorical value into numbers. So in this case, we're going to using Spark ML pipeline to actually putting into different stages in sequence, and then we're going to go ahead and run this. So since our data is already optimized in there in the Delta table, this shouldn't take much time since we haven't already do that. And what we're going to do, we're going to just take a high-level view of rough view of what the data looks like. It looks like our data having the old data inside, the original data inside, the sensor ratings, and the types, and also the additional columns with all the pre-processed values, and our indicating our scores on the value on the index itself as well. Then once the data has already been pre-processed, you're going to split the data into three different data sets. Into training data, our validation dataset and also the testing dataset. So we're going to use our training data to do the training only, and using the validation data to evaluating our model during the hyperparameter tuning stage to find out the best model. And we'll be using our testing data to serve as a real-world data set, which is unseen by any model we have trained, and use that to deploy it into a Spark streaming app we're going to go through. So before we go into the training, we're going to define a few helper functions. I'm not going to go through the details of this, but in a high level, it takes a hyperparameters you specify, and also before start training the model, we're going to start a ML flow scope. And then once inside them, we're going to create our model based on different frameworks. And then we're going to use ML flow to log the parameters, and then to log the model after the model is already trained. And also we're going to do a little bit of the metrics, finding out what's the loss of this current model. So we're going to do that by indicating an R2 score and also the mean square error. And then we're going to log them also into the ML flow. And ML flow provides you this flexibility to log everything you wanted. In our case, we also log some feature importance we're going to generate it by ourselves. Let's go ahead and run this particular function. And then this is a sample run we can actually go through to create our first ML flow models. As you can see on this particular thing, indicating this new model is being running. And if you refresh on this for some time, once it's finished, you can see what details are there. And also, ML flow provides you another console that you can dig into a little bit further. But let's go ahead and try to find out what the best model is, and then we can go back to the console and look into that a little bit deeper. So we're going to do this hyperparameter tuning. And then instead of writing a bunch of code, a couple hundred lines of code to do this on yourself on a distributed cluster, we can use the hyperopt and by importing a few helper functions to define our algorithm, which is Bayesian approach in this case, and define our search spaces and define our objective function to minimize our loss. And similarly to what we did with MLflow above, we're just putting this run within the scope of MLflow to track the particular runs. Let's go ahead and run this. So once this is getting started, it will be launching a bunch of Spark jobs because we're trying to run this Spark job as our random forest model and also train this in a distributed way on multiple models trying to do the training. And let's switch back to the console itself. If we refresh the page, you will actually see a high-level entry in here indicating that's our hyperparameter run, and all the sub-runs or nested runs will be included in here. And at the moment, there are 3 models have been already run, and you can actually see some high-level details on what hyperparameters we are using and what's their actual current score. So this might take some, let me hide this for now, since now this might take some time. What we did is we didn't take a very large run for this AppBox for hyperparameter tuning. In our case, we're only using 10. So we'll be running only 10 outbox, which means we running this particular hyperparameter tuning job trying to find the best parameters within 10 iterations. So literally, it'll be kind of give us 10 different models of random forest. And then once it's finished, we can take a further look on how the model is performed properly. Give it a sec. So the last model should be finished relatively quicker. Now, all the models have been finished. Now what we're going to do, we're going to select all of this data, all of these entry points, all of these rows of our different models we have already run, and then we're going to click on compare. Now, all this part, it offers you some visibilities, plotting out a few features on hyperparameters and see the correlations on its space and what values have been already searched and what are the performance of that particular model. And also providing some contour plots on giving you some ideas if you are actually reaching the local optima, which is one over there. There could be many optimas within the space trying to search. And most importantly, it gives you the parallel plots on every single models you have just run. And it gives you all the combinations of hyperparameters and see how the model will be performed. And also gives you the flexibility to moving around the axis to see what the correlations between two different hyperparameters. And what we're really just looking at is really this particular part here, which is right here. I can't zoom in. Right here was the lowest error rate, which have the lowest loss, which indicating that's our best model. Now let's go back to our notebook and trying to load our best model programmatically from MLflow. So MLflow provides you the tracking APIs or the features to actually let you to query your runs and load your model programmatically in the notebook or in any code you specify. In this case, we're going to use the MLflow client, and then we're going to use the functionality to search all the runs we just run in our experiments. And this will give you pretty much a very large response. But what we're really looking at is placing a filter on getting our best model. In this case, we're going to get the model with the lowest loss. And then we're going to go ahead and run that, and that will be indicating our lowest mean square error is about 0.07. Since we also logged our artifact, it could be easily picked up from the MLflow's response from the MLflow tracking APIs. And then we can know this actually the model is stored on the DBFS as well, and essentially it's on S3 bucket. Now, let's go ahead and reload our best model. So what we're going to do that, we're going to do that with the ML Spark runtime. We're going to simply load the model by indicating just a single line of code by indicating where the artifact is. And in our case, the model is now loaded, and just run a sample run to see if the model is working. We're going to do a prediction on our testing data for the first 10 records. And if you take a rough look on this, you will see the prediction as a score to indicating if there might be a failure or not at the end. Now we have our best model, and then we're going to deploy this into a streaming solution. Since we don't really have a streaming source at this point yet, what we're going to do, we're going to try to mimic a streaming scenario. So we're going to sample like 4,000 records from our testing data, which never been touched by any model, and then we're going to save that into our Delta table in a temporary location in S3. Let's go ahead and sample the data. This shouldn't take much time as we only have like 4,000 records. And then let's take a rough look on how this temporary location looks like. So we have more than 1,000 files here. So every single file will be serving as a streaming batch. We'll be streaming our data. Now, to do the streaming analysis or do the streaming processing in Delta, it's pretty straightforward. Since it's already integrated with Spark structure streaming, all we can do, or all we need to do, is using a few different keywords as indicating our Delta table and some transformation logics we're going to do. In our case, we're going to first read our temporary Delta input table as our streaming data event. And then we're going to use our model we just loaded from MLflow, or the batch model. And then we're going to do the predictions and then assign a new column name called timestamp, which indicating that's when my data is loaded and then getting transformed and predicted. Let's go ahead and run this part before we actually start the streaming job. Then we are not writing in this time. We are not writing into any sync or any downstream sources yet. What we are doing, we're going to write the temporary data into, or temporary solution, or from the model predictions into memory, and then we're going to give the temporary table a name as result, so we can query them in real time and see some data points. Let's go ahead and run this and start the Spark streaming. So this will take a couple seconds to start the streaming itself, and it will provide you a couple graphs in like this to indicating how your streaming processing and batch processing is running against how much the data is getting inputted as well. Let's give it a second, just trying to build enough data records in the memory table so we can visualize them properly. So while this is running, you can specify literally any queries in Spark SQL context like that, and then you can run this particular query to see what will be my latest records or my latest predictions from our model. In our case, for the first 20 or 30 seconds, looks good, and starting from like 10 seconds before the score, it's jumping up a little bit higher. Let's refresh it again to see if that's a normal pattern from now on. So this gives you a rough look like that, by indicating there could be a failure with a higher score, or not really a failure with a lower score. So you can also do a bunch of other aggregations on the window itself when you query the data. In this case, we can aggregate them together in a minute level. So compared to the last minute, you're actually jumping up these average abnormal score quite a lot, which might indicating my sensor or my wind turbine could be having a failure soon. And also other queries like grouping them together in hourly window, but we don't really have a data point in here since it's just one right here. So that will be the end of this particular demo. I'll be passing on to Koorosh on wrapping up this particular workshop and giving a little bit on the database itself. Koorosh? Koorosh, are you there?
Yes, I am. Sorry, I was on mute.
Yeah.
No, all good. So you wrapped up the demo. Thank you very much, Joshi. I know it was a very quick run through the demo. Obviously, going through a demo like this in a workshop, it is much better to be hands-on. It is much better to be interactive. You follow on as Joshi goes through each cell. We understand that if there is an interest to run this type of workshops, please let us know. We are planning for our events for the next 3 to 6 months. So one of the things that you will receive part of the follow-up for this presentation, this webinar, is we want to get your opinions on what would you like us to focus on next. We have a lot of great technical resources, a lot of great technical content that we can present, and in Intellify we believe in sharing. We do not want to have a big piece of pie which is small. We want to grow the pie. So if it is something that is in your mind, you want us to focus on machine learning, on data engineering, on AI, anything, please let us know. So watch out for the survey that's going to come with the follow-up with this webinar. Okay, just to wrap up, I am going to share my screen. Yeah, so we talked about building a platform, right? Building an end-to-end platform which ingests the data at one point of it and outputs a number of predictions and forecasts and inference to downstream business systems. This is the current mentality that is basically dominant in the market. When you talk to people, when you talk to data architects, ML architects, people who are doing machine learning day in, day out, what they mean by a machine learning platform is pretty much what we presented. But we genuinely believe that this is not going to be the way in short to medium term. Platforms will be replaced by a decentralized way of doing things in data in soon future. Simply because platforms, we have been working with them for the past 6-7 decades of IT. Data warehouse teams were created back in the 60s, and they evolved and they went through many different iterations and many different versions. But we are at a interesting point in the history of IT and history of data that these single owned platforms cannot scale for the needs of the organizations. Data was a byproduct for a long time. and it still is, a byproduct of a transactional system. For example, if you are an insurer, if someone makes a claim, that is a transaction that is going to be captured in your system of record. And then as a result of that, a data is being generated, being treated as a second-class citizen, find its way through an ETL pipeline into a data warehouse. So some teams, at the end, like the actuarial team or the BI teams, can make some reports and make some suggestions. If you think this is going to be the way of future, think twice, because in future, data is needed by every single department and every single customer. That's why we saw in companies like Amazon, they had a massive shift of a few things. First, introducing APIs back in 2002, introducing decentralization, going to microservices architecture, giving autonomy to the team to develop their own technology stack, basically creating that polyglot type of approach where every team was responsible for their own data and making their own data available to the other team to consume through an interface, which is basically APIs. So these are the tech giants. They had a lot of head start compared to a typical enterprise organization in Australia. But it is 2020. Since the day that Jeff Bezos made that announcement back in 2002, we are 18 years and we are still building platforms. Even you attend webinars where I tell you that you need to build a platform like this, you need to control it. It gives you some optimization. Yes, it brings data scientists closer to the developers. It brings the ML engineer closer to the data engineers. It gives you some optimizations, but it is not a step-level change. A step-level change is coming. A step-level change is something that applies the same principles of domain-driven design and decoupling and microservices architecture that evolutionize the world of development into the data. Something that we are very, very passionate about at Intellify, a concept called data mesh. Pretty much applying all of the learnings that we've had in the development world on microservices to the data. So going from centralized governance to a decentralized ownership and federated governance as code. Going from monolithic systems, such as an enterprise data warehouse or a data lake being run by a single data team, to a distributed architecture. Going from pipelines as a first-class concept to domains as a first-class concept. Again, in an insurance industry example, claims is one domain, customer is another domain, contact center could be another domain. And there are different types of domains. There are producers domains that are close to the reality of the business, close to those transactional system of records. And there are consumer domains, for example, the data science teams or the BI teams that are basically consuming the data and they generate insights. And also, as I said, going from data as a byproduct to data as an asset, data as a product itself. Stay tuned. We're going to have a lot of awesome content, a lot of awesome webinars around data mesh, which we think it is a great start to revolutionize how organizations look at the data. Data mesh is not necessarily a technical concept. It is a business transformation concept enabled by tech. And to be honest, the majority of tech that we need to enable a true utopian data mesh is not here yet. But a lot of brave customers and a lot of brave organizations who were always on the bleeding edge of technology have started looking into this and getting very, very serious about this. Because enough is enough with sinking millions of dollars into a data warehouse or into a data lake initiative and not getting the results out of it, not getting the ROI requested. The only way you can justify a very expensive, I don't want to name names, a very expensive, data warehouse to be implemented in our organization these days is to use it as a very, very expensive relational database. So if you look at your enterprise data warehouses, if you work in a big enterprise, you see They are not data warehouses used for analytics purposes. They are serving transactional workloads that are responsible for millions or even $100 million of your revenue. And that's why they can be justified. This is not going to be the way of tomorrow. Tomorrow is going to enable you to create product teams. Stay tuned for data mesh. And now I would love to answer questions if you have any questions. So we saw a few questions coming up. Joshi and I have tried to answer most of them. See any new ones? We have a few really good questions from Saurav around hyperparameter optimization, around comparing hyperparameter optimization, automatic hyperparameter optimization, like with packages like HyperOpt or SageMaker automatic model tuning, or its equivalent in Google or in Microsoft. Saurav is basically asking, can they do a better job than data scientists? Yeah, the answer is yes, they can, simply because they can scale faster and scale better and scale larger than what a data scientist as an individual or even a team can do. In just a couple of lines of code, as you saw, well, more than a couple, maybe 10 lines of code, you saw Joshi ran a hyperparameter tuning on a number of different hyperparameters, all handled by Spark runtime in MLflow. For a data scientist to be able to do this manually, we're talking about days of work, days. So if you consider all the trade-offs, yes, they can pretty much do better than data scientists. We see, and there are a lot of trends on the HPO side of things. For example, I'm hearing that Google is taking the path of using reinforcement learning for hyperparameter optimization, and companies like AWS or Databricks are taking the path of looking into Bayesian methods. There is no one-size-fits-all, but it has been proven time over time that Bayesian can do a better job than your normal random grid search or randomized search. But you know, Bayesian has its own issues as well. To hire a data scientist who knows Bayesian and who can implement a proper Bayesian implementation for HPO, you have to pay good money, very, very good money. Where, as you saw, it was just a few minutes of running a job in Spark cluster. So it is all about the trade-offs. Is there any other questions? I should have had my email up here and Joshi's, but we are monitoring info at intellify.com.au. I'm sorry, I don't have it in the deck, but we are monitoring info at intellify.com.au. Just drop us a line if you have any questions, anything we can help with, more than happy. I'm personally monitoring that for the next 2 or 3 weeks. If you have any questions, and beyond that, there are definitely people in the team looking after that email. So glad to have you here in this presentation, and I hope it has been a good use of your time, and I hope you learned something new, and I hope what you learned does not contradict reality. Fantastic. So since that we don't, oh, maybe there's some new questions. We had quite a few questions on feature store. No, we didn't use a feature store functionality on this exact demo. We are thinking about running a complete full webinar workshop on feature stores. The solution that we fall in love with was HubSpot from a company out of Sweden called Logical Clocks. They have a really nice, neat solution that integrates really well with Databricks, with SageMaker, and with a bunch of other tools that you can run as a feature store. You calculate your features, you put them into groups, you advertise them, you can search for them. It is an amazing tool. We are thinking about running a session on feature store. But as I said, feature store was created as an initiative by Uber. So if you've not heard about Michelangelo was the name of the platform that Uber created internally to do machine learning at scale. So the people who created that feature store functionality in Michelangelo have left Uber and they started a company called Tekton.ai. I will put that in the presentation deck that we will send you. Tekton has a really interesting solution as well. Let's see which one is going to be dominant in the market. Who knows? Maybe in the next reInvent, we will have a feature store from Amazon. Maybe in the next Spark Summit, we will have a feature store from Databricks. We had a few questions on the presentation. So definitely you will get the slide deck with a little bit more detail in it. And also the source code of Josh's demo. For the recording, to be honest, we have not made a decision yet to either publish this recording or not, but most likely the answer is yes, and you will get a link to an on-demand view. And thank you, Dave, for your great feedback. Thank you very much. Thank you, Saurav. And yeah, I think we have covered most of the questions. Yeah, if not, please reach out to us directly. Okay, thank you very much, and have a great weekend, everyone.
Thank you.
Happy Friday.